Okay, so you've got to be wondering, right? How on earth did the AI tools we use every day go from being kind of clunky and, well, basic, to suddenly feeling like you're talking to a super intelligent being? It feels like it happened overnight. Well, let's get into it, because this incredible progress isn't an accident. There's a secret formula.
So what's the deal here? Is it some, brand new secret algorithm nobody's heard of, some flash of genius from a single researcher? The answer, it turns out, is actually way simpler and at the same time way bigger than you might think.
You see, it's not magic. It's a recipe. Back in 2020, researchers at OpenAI dropped this landmark paper, Scaling Laws for Neural Language Models, and what they found was wild. They discovered that making AI better isn't some chaotic random process. Nope, it follows a surprisingly predictable recipe, a set of rules for how to make these things more and more powerful.
And like any good recipe, it all starts with the ingredients. These researchers pinpointed 3 key factors that, when you turn them up, reliably make the AI perform better. This whole idea is what we now call scale.
So what are these magic ingredients? It's these 3 things: the size of the AI model itself, the size of the data set it learns from, and the amount of pure computing power you throw at it. Let's break down what each of these really means.
All right, first up, model size. Scientists call it N. The best way to think about this is like the number of knobs and dials inside the AI's brain. Every single parameter is a little knob that gets tuned during training to help it spot patterns. So the more knobs you have, the more intricate and subtle the patterns the model can learn. And we are talking about billions of them in today's models. Billions.
Next, we've got data size, or D. This is basically the AI's library. It's all the books, all the articles, the entire internet that it gets to read to learn about, well, everything. For these language models, we're measuring this in trillions of words, or tokens as they're called. It's just a mind-boggling amount of information.
And finally, there's compute, or C. This is the engine. It's the raw horsepower. It's thousands of specialized computer chips running red hot for weeks or months on end, doing the actual work of turning those billions of knobs based on trillions of words. It's just an immense, immense amount of energy and time.
Okay, so we've got our 3 ingredients. But here's the thing. The real magic isn't just in the ingredients. It's about how they all work together. This is where the laws part of scaling laws comes in, and it reveals this incredibly clear path to making AI better.
Now, the key word in that whole sentence, the word that changed everything, is smoothly. This was the big aha moment. Progress wasn't just a lucky break here and there. It was a predictable upward curve. You add more data, the model gets better. You throw more computers at it, it gets better. They had found a reliable dial they could just turn up.
This predictable relationship is something scientists call a power law. But really, all it means is for every bit of effort you put in, more data, more compute, a bigger model, you get a predictable amount of improvement back out. All of a sudden, the path to smarter AI wasn't some confusing maze anymore. It was a mountain to be climbed, and they had just drawn the map.
And this right here shows the massive paradigm shift this caused. For years, the whole AI community was hunting for the next clever algorithm, the next big architectural idea. But this research suggested that, at least for now, the main path forward was just get bigger. Predictably, systematically bigger.
But here's where the recipe has a really surprising twist. I mean, you'd think that just getting bigger and bigger would be incredibly wasteful, right? But the research found something totally counterintuitive about efficiency.
Just think about this for a second. Let's say you have a certain amount of computer power. What's the best way to use it? Do you take a kind of small model and just train it for a super long time, like a year, until it's learned absolutely everything it can? Or do you build a massive model and only train it for, say, a week?
The answer is kind of shocking. It turns out the most efficient thing to do is to build the biggest model you possibly can and then stop training it long before it's finished. You don't train it until it's squeezed every last drop of learning from the data. You actually stop it early. Why? Because these huge models are what's called sample efficient. They just learn so much more from every single piece of data they see. Think of it like this. A smaller brain might need to see something 10 times to learn it. A really big brain, it gets it on the first try. That's why a gigantic model trained for just a week can actually be smarter than a smaller one trained for an entire year. Bigger isn't just better, it's actually faster.
So this surprising discovery about efficiency brings us right back to that third ingredient, compute.
Because to build these bigger is faster models, you need an absolutely insane amount of processing power. And this isn't just a number in an equation. It's a revolution built on very real, very powerful hardware.
The ability to scale up compute is what unlocks this entire recipe. And this horsepower doesn't just come from thin air. It comes from these massive data centers packed with thousands upon thousands of specialized computer chips, usually GPUs, that are designed for exactly this kind of work.
So, for example, a key piece of hardware from that time was the NVIDIA V100 GPU. A single one of these little chips could perform 125 trillion calculations per second. It's just a staggering number, and that's what it takes to even begin to tune all those billions of parameters we talked about.
And the pace of this improvement is just relentless. That one chip, the V100, was 4 times more powerful than the one that came before it. This constant exponential growth in pure hardware power is the fuel that keeps these scaling laws going.
And of course, you never use just one. When you stack just 8 of these chips together in a server, it could chew through almost 8,000 images every single second. This is the real-world engine that makes the abstract idea of scaling into the AI tools that are changing our world.
So let's bring all this home. We started with a mystery. How did AI get so smart, so fast? And we found a surprisingly clear answer. The big takeaway is this. Right now, progress in AI isn't really about random flashes of brilliance. It's about the methodical, predictable process of turning up the dials on those 3 key ingredients: model size, data size, and compute. More isn't just better, it's predictably better.
But this leaves us with a huge, critical question for the future. We found a recipe that works, but the ingredients are getting astronomically expensive. Building and training these models cost hundreds of millions of dollars and uses the energy of a small city. So, what happens when we hit a wall? What happens when we just can't afford to get any bigger? What comes next?